having trouble finding that. And so I'm gonna, I gave you an announcement on D2L about the first one, but the next one, from now on, I'm just gonna assume that you will be checking. It's generally once a week. We have the D2L quiz off of D2L. As a reminder, right, I'm trying to keep things easy for you. I will drop the 2 lowest quiz scores at the end of the semester. So maybe this one by accident. So there's no downside here because you get 2 weeks free through Mastering Astronomy, even if you are waiting for an access code to arrive or something from a bundle that you ordered on Amazon. So go through and get, 25% of your grade is homework, and all the dates are listed there in a calendar on Mastering Astronomy. Are there any questions before we get to the lecture?
Are we able to look at our quiz?
Sorry? Two people talked at once, so.
Yeah, sorry. You can go ahead.
Oh, sorry. Are we able to look at our quiz, like what questions we got wrong?
If you have a question about which questions you got wrong, why don't you send me an email? Right now, the way D2L has it, I don't think I'll make sure you can if you don't already. And for the first week, if you send me a question, I'll send you I'll send you which questions you got wrong and what the right answers are. Let me put that on my list of things to make sure that you can see that.
Okay, thank you.
Sorry, what was the other question?
For the homework, so would we still be able to turn it in after it's late?
So anything completed after the due date is not counted, but if you complete like half of it before the due date, it'll count half of it. And you're still able to access them, and you can go through them as much as you want, but you won't be counted after any time it's done after the due date.
Okay, thank you.
Any other questions? All right, so we're going to talk a little bit about the history of the origins of astronomy and how we got to where we are in terms of understanding that the sun is the center of our solar system. Before we get into new material, let me just ask a few questions, make sure that you still have some things in your memory from the last couple lectures. One is, what is the ecliptic? This is something I'm going to be saying repeatedly, the word ecliptic. What is the word ecliptic? I'm going to answer this one myself. It's the path the sun appears to trace around the celestial sphere each year. If you imagine the celestial sphere, all the stars, the Earth is in the center of the celestial sphere spinning. Its equator extends out into space, cutting that celestial sphere in half. But the ecliptic is not on the equator because the Earth is tilted relative to the Earth-Sun plane, which is the same thing as the ecliptic. So because of that, the sun follows the ecliptic around the celestial sphere each year. Half of the year it's above, illuminating more of the northern hemisphere. Other 6 months in winter, it's illuminating more of the southern hemisphere. Okay. There's another question. This one's from last lecture. So full moon on the meridian, meaning, so remember that the meridian is a great circle passing from the south to the north, extending through your zenith. And at approximately what time would a full moon be on your meridian? Okay. Essentially think of a moon straight ahead, above you. Okay? What time would you see a full moon straight ahead? Well, it would be midnight. And the reason why is because at midnight, you are facing away from the sun. You're on the side of the Earth facing maximally away from the sun, right? And in order for you to see a full moon, the moon has to be maximally away from the sun from you. Okay? So it makes sense that on midnight, you're standing on the far side of the Earth from the sun. So if you look straight up, you will see the full moon. This gets back to that diagram. If you don't kind of remember this, there's a cartoon I showed you last time showing you the phases of the moon corresponding to where you are standing on the Earth and where the moon is relative to the sun. Okay, here's one kind of putting some of that information as well to the test that I'll ask. So let's see if that's my thing not coming up. Here it is. I'll ask a poll question here. All right, what conditions are required for a solar eclipse? Let me bring back the. I'll let you read it.
Mm,
Yeah, okay. 10 more seconds to think about it. Okay. So most people did get it right. So this is kind of the opposite of the last question in that if it's a solar eclipse, that's the moon getting between the Earth and the sun, right? If the moon's going to block out the sun, it has to be between the Earth and the sun. And that's the conditions for a new moon, right? If the moon is on the sun side of the Earth, then what you're looking at is not illuminated. It's the shadow side of the moon. And then also, in order for the eclipse to happen, not only does that have to happen, but the moon has to move into the ecliptic plane, meaning the nodes of the moon's orbit must be aligned with the Earth and the sun. Now, the other similar answer is the last one. The phase of the moon must be new, and the moon's orbital plane must lie in the ecliptic. But that's just not true. The moon's orbital plane is not in the ecliptic. And that's why it's rare to have a solar eclipse, because it has to pass through the ecliptic and one of those what we call nodes. In other words, intersection between its path and the ecliptic. Okay. So, ancient roots of science. Let's go talk a little bit about history and how people came to understand our modern view now that the sun is the center of the solar system. And even as we'll discover, right, that's not the end of it, right? It's a vast universe with billions and billions of different solar systems, right? And we're not particularly special in our relation to it. And the development of that understanding is through scientific thinking. We observe, right? We don't just think what we think might be beautiful or what we think would make sense. We observe, we think critically about what we observe, and we do experiments, right? We really want to check whether our predictions about when eclipses are going to be, what are the path of the planets and the stars, right? On what dates and times do you expect things to happen? When are the seasons? All of these things, you make predictions and you see if they're true. And early astronomy, so I ended last lecture with this example, just to, first of all, remind you that these people were not stupid. They're very smart. In fact, a lot smarter than some people these days who think the Earth may be flat. Right? Except about 200 BC, Eratosthenes not only showed the Earth was round, but calculated quite accurately its circumference. And so you saw that video last time, and it's based on the idea that if the Earth's surface is curved, then two sticks pointing up towards the sun have different length shadows. But going back, right, so to what we started discussing in the very first lecture, one of the first major observations you have on Earth that everyone can observe is that every night you can watch everything in the sky rotate around, not just the moon and the sun, but the stars. And this is a time-lapse photograph showing that if you just put a camera up for a few hours and let it do a time-lapse, you see the stars are all moving around. And here in this case, they're moving around Polaris, the North Star. So that's the North Pole of the Earth that that's pointing towards. And we now understand that this is, because Eratosthenes, right, showed that the Earth was round and it had a given radius. We can imagine that if the Earth is spinning, then it looks like everything's rotating around us, right? And that's what we understand to be the case. But back then, they didn't really, that didn't make sense to them. It wasn't because they were stupid, but they thought that if the Earth was spinning, we should feel it, and there should be strange effects that we would measure that they couldn't measure, okay? Because their understanding of physics and science hadn't progressed to the point that we understand it today. But there were all sorts of ideas. And so here is astronomers in the age of antiquity that starting, even before Pythagoras, but Pythagoras, for example, 600 BC had ideas about planets orbiting a common center on kind of circular paths, and similar ideas to what we'll talk about in a second. But some of these, even before then, some of them in other cultures in the East, had all sorts of ideas, spanning everything from what we understand today, that the Earth, that the sun was the center of our solar system, to the idea that the Earth was the center, planets moving around in various ways in kind of solar system-like patterns. But it wasn't until about 300 or 400 BC that people began to come up with, the Greeks in particular, came up with detailed predictive models that you could use to say, oh, the stars, these planets that we can observe are going to follow very specific paths that we can calculate using math. And so the very first major model we call the Greek geocentric model. This was Plato's and Aristotle's. And it said that, okay, we don't feel like we're moving. It doesn't look like we're moving to us. Let's just say that the Earth then is fixed. It's the center of the universe. After all, we're special. The Earth appears to rotate from east to west every day. And we'll talk about something called stellar parallax. They had a reason, a definite reason why they thought they could prove that the Earth was fixed. Okay, and we'll talk in this lecture about stellar parallax that they did not observe. It turns out it's because stars are way farther away than they imagined. Okay? And they had a kind of a prejudice for simplicity for circles being perfect. This is something to that the Greeks had a bias here that planets had to move on perfect circles. And it turns out that one thing we'll talk about in science is not clinging too hard to what you think might be beautiful, and instead letting observations really lead the way. So here is the Greek geocentric model, or cosmology, you might call it, where the Earth is at the center of the universe, and then various what they called planets, so that included the moon and the sun, orbited the Earth on what they call these crystalline spheres. So these perfect spherical, in other words, circular motion around the Earth, the moon, Mercury, then Venus, then the sun, then Mars, then Jupiter, and then Saturn. That's all the planets they knew. And then the stars were the last thing on the crystalline spheres. And these were all rotating around the Earth at different rates. Okay? And this actually made predictions, and it actually worked pretty well. I mean, they could actually predict when planets were going to be in certain places, when stars would be in certain places. But there were some complications. So one major complication is that planets can go into what's called retrograde motion. So here's a path of Mars. Every couple of years, Mars is moving across the sky with respect to the stars. Okay. Now we now understand this because Mars is in an orbit, right? And the stars are basically fixed out there. And so against the stars, Mars is moving over its few-year orbital period. But every couple of years, we see the path of Mars slow down to actually speed up and then slow down and then go in reverse and then continue on its path. So it's moving around just like normal, and then suddenly speeds up and then goes backwards and kind of flings around in a loop, which is very weird. So how, if Mars was on this crystalline sphere just going around the Earth, how could it possibly reverse and start going backwards? And this was very weird. And in order to account for this, the Greeks invented what are called epicycles. Now, Ptolemy is the one most famously associated with this. I mean, like I said, though, the Greeks had all sorts of cool ideas spanning back hundreds and hundreds of years, but the first really detailed model was Ptolemy's. And what they did is they added, so here's the main circle that it's called the deferent, the main circle that the planet, say Mars in this case, orbited around the Earth. But then they added a circle within the circle. So in addition, Mars had another circle that it orbited on. Okay. And it was also even a little weirder because they had something that controlled the speed of the. It was a little bit weird. Circles within circles, but it actually worked. It could predict Mars's retrograde motion, and actually was very predictive. In fact, for hundreds and hundreds of years, it was better than any alternative in terms of being able to make predictions. So let me just speak through this question because to make sure it cements in your mind what this means. So most objects in our sky appear to rise somewhere on the east and set somewhere on the west. And this is because we now understand the Earth is rotating. And if you observe from one light night to the next, however, planets appear to move from west to east against this background of stars. Slowly, day by day, because planets are orbiting. What happens during the retrograde motion of the planet? Suddenly the planet, typically over a few days or sometimes even months, actually starts to reverse and moves westward with respect to the stars. So it goes opposite its normal motion for a few days and months. That's retrograde motion. And the Copernican revolution is the name we give around the 16th century for the major developments of shifting away from this basic description of given by the Greek cosmology, where that we call geocentric, everything orbiting around the Earth, to one where we favor all of the planets orbiting the sun, not the Earth, and the sun being the center of the solar system, not the Earth. Okay? It's called the Copernican revolution. And it was Copernicus, around 1500, that produced the first detailed predictive heliocentric model. So that has the sun at the center and all the other planets orbiting around the sun. Now there's some that wasn't perfect. We'll get to improvements on this. So he still had planets orbiting in perfect circles, for example. So it wasn't ideal, or it wasn't perfect, but it was a major change that, for example, as we'll discuss, solved this retrograde motion of Mars without adding an epicycle to do it. And to understand how it's actually really beautiful how we can understand that weird motion of Mars without adding any epicycles as purely due to an effect of perspective, if you assume this one idea that the sun is the center of the solar system, everything else falls out naturally. Okay, and the way to understand how you naturally then see that Mars will have this retrograde motion every couple of years is by understanding what's called parallax. Now that sounds like a fancy word, but all it means is something you're all very familiar with, which is that, if you're driving on the freeway and you drive by a grain silo like this, the grain silo moves across your field of vision, whereas the things that are further away don't move very much. In fact, the closer things are to you, like a fence or something, flies by, whereas further things like the silo go by more slowly, and then the mountains in the distance go by really slowly, and then the sun in the back just stays there. That's called parallax, the shifting of things in your field of view that are closer to you when you move. Okay. You can see that right now. If you put a hand here and a hand here and you shift your head, the hand closer to you moves more in your field of vision than the hand farther away. And this is a beautiful idea because if the Earth is moving around the sun, then every year the Earth travels all the way from one side of the sun, and then 6 months later is on completely the other side of the sun. The Earth has moved very far. So things that are closer to us, like say planets compared to the stars that are further away, are going to shift relative to those stars in the front of us. Right? So say in June, you're over here looking up towards Mars, and it looks to be here with respect to the stars far behind it. Just like a car driving by that grain silo, 6 months later, the Earth has moved very far, and now you're looking from this side of Mars, and it's in a totally different location in the sky. And that's not because Mars has actually moved; it's because you've moved and you've changed perspective with regard to Mars. So that's called parallax, and that's actually explains two things. It explains why Mars appears to go in retrograde motion, but it also is important to something we'll talk about later, which is why the Greeks even, way back then, thought they had proof that the Earth was fixed. It's because they didn't see stars moving when over 6 months of the Earth moved. But they didn't have any idea that the stars were so far away that their ability to see, because they didn't even have telescopes back then, the stars were so far away that they couldn't see with the naked eye stellar parallax. We needed much better equipment to be able to measure it, and we can now. So here's how you understand retrograde motion. So now, if the Earth was over here in its orbit, so the Earth is blue and Mars is red, and they orbit going around counterclockwise. So every year Earth does this, right? Every couple of years Mars does this. And so if Earth is way over here, you're just looking up in the sky and you see every day Mars moves a little bit more further against the stars. But every couple of years, Earth whooshes by inside like a racetrack. Earth's orbit is faster. Planets closer to the sun are moving faster. It whooshes by Mars, okay, over a period of about a month. So as Earth whooshes by Mars, it's just like a grain silo. You see this effect of stellar parallax. You see Mars appear to shift in the sky. So as you say you start here, as you move this way, and you're looking towards Mars, you see Mars start to accelerate to the left, and then it starts moving in reverse direction. As you pass Mars, you start to have to look towards the right against the stars to see Mars. Okay? And so that explains just this shift, this effective perspective explains the motion of Mars without having to add any complexity to the theory. You don't have to add epicycles or anything. It just naturally falls out of the theory. It's actually beautiful with no more assumptions than before, actually fewer assumptions than before. The theory explains the motion, this weird feature of the motion of the planet. And this brings up, one way of assessing, a philosophical tool to assess. You have two competing theories, right? One was the geocentric model that had everything orbiting the Earth, but you had to add epicycles. And the other was the heliocentric model, all the planets orbiting the sun, and you don't have to add epicycles. So Occam's razor says, if you have two competing theories that make exactly the same predictions, and at that point in the 1600s, they both made about the same predictions because we didn't have good enough telescopes to do any better, you should prefer the simpler model. Okay? As Albert Einstein said, simplify things as far as you can, but no further. Okay? And you can have arguments about this. In fact, later on in the lecture, I'll give an example of Kepler arguing about this with someone. But I think most people would agree that, at least nowadays, the Greeks had a prejudice for circles, so they would disagree. But a prejudice for Earth being at the center and circles and things. But nowadays, this one assumption of the sun being the center is considered a lot simpler than having the Earth be the center, but also have to have epicycles. So that both theories can make the same predictions back then. One is simpler. Okay? So this is one reason why heliocentrism began to be favored. But again, there are issues which we'll talk about, like stellar parallax was one big example. Why didn't they see it? Well, they thought they should see stellar parallax as the Earth moved relative to the sun. Let me just make sure you're following along. So I'll ask another poll question, this time about Occam's razor. Right, the principle of Occam's razor states what? All right. Okay, most people did well. So in explaining natural phenomena, the simplest explanation, consistent with the observations, is to be preferred. It doesn't mean it's right, but if you have two theories that both make the same predictions and one's adding extra complications, it's generally a good idea to go with the simpler theory. That's Occam's razor. Another person in the story around the Copernican revolution is one of the early advocates for the Copernican heliocentric model, Giordano Bruno. And Bruno had the idea, I mean, this is a beautiful unifying of things, right? So you see all these stars in the sky, and you imagine, hey, if it's the sun that's the center of the solar system, if it's a heliocentric model, and we're just orbiting the sun, well, look at all those stars. Well, those are just probably faraway suns. Those are probably all their own solar systems. Well, the sky is just littered with thousands and thousands of faraway suns that look like points of light to us. And that's, by the way, it was an idea, again, the ancient Greeks had every kind of idea. So Anaxagoras, Aristarchus had this idea too. But this was a big proponent around this time to help push forward the idea of heliocentrism. He was, as a common theme here that we'll see, he was burned at the stake after the Roman Inquisition found him guilty of heresy. So you see this theme in the history of science where, of course, you have dogma that you're pushing up against. People with strongly held beliefs, and when the data starts to shift against that dogma, the scientist might be trying to follow what nature is telling us, but other people may want to believe things in contradiction to the data. And this is a kind of the heart of good science, is following the data, not clinging too hard to what you want the data to show. Right, so this is the idea, as a reminder, of what we might call the scientific method. This is a very simplified idea of science, and I think it gets the basic point across, which is that you don't want to just sit here in theory land. You don't want to just think that you have a beautiful idea. You make predictions, okay? And then you hold yourself accountable to those predictions. You don't, if the predictions are wrong, you don't make up excuses. You correct your model, correct your thinking based on that, and then you come up with new theories and new predictions. And one example of the scientific method that leads to kind of the modern view of our solar system was Tycho Brahe. Now, so let me make a nice quote from him when he was just 17, something to aspire to here. He says, "I've studied all available charts of the planets and stars, and none of them match the others. There are just as many measurements and methods as there are astronomers, and all of them disagree. What's needed is a long-term project with the aim of mapping the heavens conducted from a single location over a period of several years. Now you can imagine part of what he's getting at, right? If people are taking data from different locations at different times, there's no standardized clock system. I mean, it's very confusing, right? Because things look different from different locations and at different times. And he set out, now he didn't have a heliocentric model, as we'll discuss, but nonetheless, he was a good scientist. He was meticulous, and within his geocentric model, he recorded detailed data on the positions of planets and stars, and his assistant Kepler went on to kind of cement this revolution in astronomy by using this data. And in particular, one of the most important pieces of his data was this, the motion of Mars that included that retrograde motion. So here's the motion of Mars seen, its position in the sky over many, many years. It has these wonderful data points. And what you see is Mars moving back and forth. This is focusing on these cases where Mars, its motion is going back and forth due to the retrograde motion. Okay? And this is wonderful data, extremely meticulous, excellent data that is able to discern small differences between the heliocentric model and the geocentric one that kind of patched things up with the epicycles. And here, this was his geocentric model. So things had developed in order to try to accord better with the data since the Ptolemaic model, in which the Earth was still the center and fixed, but you actually did have most of the planets orbiting the sun. It's just that the sun then orbited the Earth. So it was like a hybrid model. The sun orbited the Earth, but everything else orbited the sun. And then the stars rotated around the Earth. So kind of a funny mixture of things. Still geocentric in that the Earth was the center and the Earth was fixed. And right, why did very smart astronomers like Tycho still believe that the Earth was the center and the Earth was fixed? Well, it's because of stellar parallax, right? This idea that things that are closer move when we move, and things that are further away stay fixed. And so these were smart people that reasoned that as Earth moves every 6 months from one side of the sun to the other, we should see closer stars to us shift in the sky relative to distant stars. It should have been like a three-dimensional effect where you're seeing closer stars fly by us and further away stars move less and so on. But they never saw that. And part of the reason they thought stars were close enough for us to see that is because their telescopes were bad and they made things look fuzzy. And so they thought that they could see the thickness of stars when really they were just looking at points of light that were blurred. So they thought the stars were a lot closer than they were. So that was fixed with building better telescopes. Okay, so put in concrete terms, he believed the geocentric model because he couldn't observe any stellar parallax. His observations were good to 1 to 2 arc minutes. Now, an arc minute, remember, is a 60th of a degree. Remember, the moon is about 30 arc minutes. So we're talking about a 30th of the width of the moon. That's how precise he could view things in the sky. But we now understand the stars are so far away that a stellar parallax is less than an arc second. Okay, so he was more than 60 times not accurate enough to see stellar parallax. Okay? It was only a few hundred years later that we had telescopes good enough to see stellar parallax. And now we have satellites that measure all the stars in our galaxy pretty much, their stellar parallax, to find out exactly where they are. That allows us to find out their distance, as we'll talk a lot about in a future lecture. So Tycho was a great scientist, even though he had, and just because people had geocentric models did not mean they were bad scientists. But Kepler was also an excellent scientist. He was a German astronomer who worked as an assistant to Tycho. And he looked at Tycho's data for Mars and its motion across the sky and found that it didn't quite match up with Tycho's or any of the geocentric models. Okay, and here's a quote from him. He said, "If I had believed that we could ignore these 8 minutes of arc, meaning 8 arc minutes difference between his calculations from the geocentric model and the reality he saw," he said, "I would have patched up my hypothesis accordingly. But since it was not permissible to ignore, those 8 minutes pointed the road to a complete reformulation in astronomy." Okay? In other words, he just very precisely looked at the data and found a new model in which not only was it heliocentric, but that the planets didn't move in perfect circles. Okay? He came up with a model in which the planets moved in ellipses, which are essentially ovals. Okay? We'll talk in more detail about what that means in a second. Okay? And so he formulated his 3 laws of astronomy that are correct. Okay, they are now understood to be correct, and we'll see later that they actually fall out as a consequence of Newton's laws, which are also correct. Okay, but he was the first to come up with like the correct model just by very carefully studying the data. So heliocentric model, all planets orbiting the sun, and planets don't orbit perfect circles; they orbit in ellipses. So these are his laws. We're going to go through them in detail. 3 laws that are still true. Okay, orbit of every planet is an ellipse in which the sun is located at a focus. That's just a mathematical. Every ellipse has what are called foci or focuses. Okay, so the planet doesn't orbit the center of an ellipse. Okay, it orbits one side of the oval shape. Okay. But by the way, a circle is a type of ellipse, so a planet can orbit in a circle, but in reality, they are all slightly oval shaped. Okay. The next law is the law of equal areas. A line connecting the sun and a planet sweeps out equal areas in equal times. We'll explain that in more detail in a second. And then the harmonic law. That's at the square of the period. In other words, a period is how long is a year for a planet, how long it takes to orbit the sun. So how long it takes to orbit a planet to orbit the sun squared is equal to the cube of its average distance from the sun. Okay. So these are his laws that correctly describe the motion of planets around the sun. And here's just a cool quote I dug up, where there's disagreement between Kepler and someone else who was arguing for the geocentric model, arguing about basically Occam's razor, right? What is simplest? So I think that's a pretty funny quote. "You discredit my oval path. I hold up to you the 100 times more absurd epicycles. If you are angry that I cannot eliminate the oval path, how much more ought you to be angry with the epicycles, which I abolished? It is as though I have sinned with the oval I have left, even though to you all the rest of the ancients did not sin with so many epicycles. This is like being punished for leaving behind one barrow full of shit, although I have cleaned the rest of the stables." So it's an argument about what's simpler, right? Kepler is saying having a elliptical path is way simpler than having perfect circles, but having to add epicycles. But the person he's arguing with is arguing that, hey, ovals are ugly, circles are simple. Okay, I think Kepler kind of wins this argument, but nonetheless, it's not so easy, right? You have to. There's real arguments here. There's real grist for discussion. Okay, and by the way, before I go into a little bit more detail on Kepler's laws, let me just give you an overview kind of the various planetary models there were out there. Because it wasn't, the reality wasn't just, simple heliocentrism and then suddenly geocentrism. There's lots of smart people grappling with these issues for over 1,000 years. And these are the detailed models, right? The ones where people were really calculating stuff precisely. So we talked about the Ptolemaic model, started around 200 AD. You had a fixed Earth in the center, geocentric, fixed Earth in the center, and then there are these circles plus epicycles. So everything followed a circle, and then epicycles, little circles within the circles. But then there's a period of 1,600 years where people tried to make things better. And so a lot of them had these hybrid models where, maybe Mercury and Venus circled the sun. but everything else orbited the Earth, and Earth was still in the center. There was the Tycho's model we just talked about, where the sun and the moon circled the fixed Earth, but everything else orbited the sun, and the sun orbited the Earth. And then there are other models also where they did, in fact, think that maybe the Earth was rotating, because it makes sense that rotating Earth can explain simply why everything else appears to rotate around us, right? Still, though, people argued because they thought that if the Earth was rotating, then there'd be experiments that we could feel it in some way, and they couldn't measure that. And it wasn't until Newton that everyone started to sort those things out. Okay, finally, there were these heliocentric models. There was the Copernican heliocentric model, where still it wasn't quite right. It was still circles. There were even still epicycles, although they weren't needed to explain any major things, but he still needed them to make the measurement, the data fit the theory. And it did have the Earth rotate. So the Copernican revolution still wasn't perfect, but it was Kepler then finally who really came up with a model in which you have elliptical orbits, no epicycles, Earth rotating, basically the modern view around 1600. Any questions so far? All right, so we're going to move forward from the Kepler model, where let's talk about what an ellipse is. Okay. It's kind of worth knowing just that an ellipse isn't just a totally random, hard to remember mathematical equation, although I'll give you the equation in a second. It's a conic section. It's a section of a cone. So if you slice a cone sideways, like shown, and you get this like green oval shape, that's in the ellipse. All ellipses can be described as slices of cone. You can have a horizontal slice that makes a circle, a sideways slice that makes an ellipse. So here are some examples. You slice horizontally, you get like a circle. You slice more at an angle, you get more and more of a oval, more and more ovally ellipse. If you slice like this or kind of vertically, you get parabolas and hyperbolas that are actually also part of what can happen. Those aren't orbits that keep coming around, but you do have real orbits, not orbits, trajectories that can slingshot around, what are called hyperbolas or parabolas. So these are all the family of trajectories that are described by slicing through cones in these ways. Mathematically, I don't expect you to remember this, but this is the formula for an ellipse. And there's what we call the eccentricity. So if you have an eccentricity of 0, that's a circle. But if you squash down that ellipse, the eccentricity increases. There is, for example, a pretty large eccentricity, 0.9. Okay? Most planets look closer to circles. They have small eccentricities. So most planets actually look more like this, small eccentricities, where it's a little bit hard to tell whether or not it's just by eye. They kind of look still like a circle. Okay, so that's the first law, the law of ellipses. All paths of planets are some kind of an ellipse. The next law is this equal area law, okay? He says that if I draw an imaginary line between, so here's the sun and here's a planet orbiting the sun, right? So you have an ellipse. The sun is at what we call the focus of the ellipse. So the planet can get far away from the sun or can get really close to the sun on the other side of the ellipse. And if you draw an imaginary line between the sun and a planet, it sweeps out equal areas in equal times, meaning when the planet is far away from the sun, the planet moves slowly, meaning if you wait a day, the planet moves slowly so that the area carved out, shown in green here, is the same as if you wait a day and the planet's really close to the sun, it has to carve out the same area in that day, meaning it has to speed up and whoosh around this side of the sun so that in one day it moves much further to carve out this area shown in green. That has to be the same area as that shown on the left. So you can think of it as equal areas in equal times, or if it helps, you can think when a planet's far away from the sun, it goes more slowly, and when it gets close to the sun, it whips around more quickly. That's another
less precise, but that's the right idea. And this is actually a consequence of angular momentum conservation. This is another physics concept we'll talk about in more detail later, but angular momentum is mass times distance that you are from something times velocity. So distance times velocity here is conserved, meaning it doesn't ever change. So if I get close to the sun, the distance r is much smaller. So in order for distance times velocity to stay the same, the velocity has to increase. So at the end of the day, this second law of Kepler says, again, if you're far away from the sun, you go slowly. If you get close to the sun, you whip around quickly. That's Kepler's second law. Kepler's second law, which states that as a planet moves around its orbit, it sweeps out equal areas and equal times, means that a planet travels faster when it is nearer to the sun and slower when it's farther away from the sun. Okay, his third law tells us how, if a planet is a given distance from the sun, how long is a year going to be? In other words, it tells us essentially that the further you get from the sun, the longer a year is. You go more and more slowly around the sun. Let's look at the numbers here. This is the orbital properties of the planet. So Mercury is the closest planet to the sun. Neptune is the furthest from the sun. And here's their distances from the sun, okay? In AU, meaning astronomical units. So Earth is 1 astronomical unit from the sun. In other words, Venus is about 70% of the Earth to the sun. Mars is about 150%, and so on. As you can see, the year on each planet gets longer and longer. So for Mercury, it's about a quarter of an Earth year. So in other words, Mercury circles the sun every 3 Earth months. But if we go down to Neptune, it takes 164 years for Neptune to go around the sun. Okay. And then we can calculate the speed. We see Mercury is going the fastest. It's whipping around the sun. And Neptune is very, very slow. Okay, and we can quantitatively, what Kepler's law says is the period, how long a year is, squared is equal to the cube of the average distance from the sun. Okay. So if you just plot the periods of the planets on the y-axis, the average distance on the x-axis, they all line up along this beautiful, just perfectly, beautifully on this curve given by p squared equals a cubed. And what this means is that the further away a planet is from a star like the sun, the slower it goes. So here's the curve of, so on the x-axis we have distance. So Mercury is closest, is furthest to the left, and Neptune's on the is farthest, it's on the right, and velocity is on the y-axis. So Mercury is going fastest, then Venus, then Earth, then Mars, and Jupiter, and Neptune's going the slowest. And by the way, you can calculate this with what you know. I'm not going to make you do it, but I just want to show you that given what you know, you can actually calculate this, right? So we know that velocity times a period, p, and here I'm just going to relabel that, we usually call that t. So velocity times the time to go around one period is the time to go around the sun. So velocity times time is distance, right? Velocity times time is distance. That's one of the basic physics rules. And the distance it travels is 2 pi r. That's the circumference of a circle. So 2 pi r, okay? And from that, we can just plug in, right? That means that velocity has to be 2 pi r over the period, okay? And from Kepler's law, period squared is r cubed. We then get the velocity is 2 pi over the square root of r. So that's where this curve comes from. Okay. So here's the sort of question that I would expect you to get on a quiz. So this is like the sort of thing I expect you to be able to answer. So math is not heavy in this course, but this is about as far as it goes. So from Kepler's third law, p squared equals a cubed, okay? And I want you to be able to then answer a question like, you have an asteroid with an orbital period of 8 years. So p is 8. Okay. What's its average distance from the sun using Kepler's third law? Well, 8 times 8, so 8 squared. 8 times 8 is 64. So you need to find a times 8 times a, that's 64, right? Because 8 squared is a cubed. So the answer is 4, okay? 8 times 8 is 64, but 4 times 4 times 4 is also 64.
Oh.
So if you know that an asteroid has an orbital period of 8 years, you know its average distance from the sun, which is really useful. You know, it's about 4 astronomical units away. Now, one of the tireless advocates for the Copernican revolution, the heliocentric Copernican model. Now, he was about at the right time, but he advocated for the Copernican model rather than the Kepler's model, but he had the basic right idea, which is that, you know, he made arguments and experiments that kind of knocked down most of the geocentrists' arguments, okay? So one of the things that, going back to Aristotle and Plato, that they argued, hey, was that the Earth can't be rotating because we would feel it, right? We would be left behind. If we jumped, we would fly off the Earth or something. But he showed something that presages one of Newton's laws, that moving objects remain in motion unless acted on by a force. In other words, if we're on the surface of the Earth, we don't, even though the Earth is rotating, we don't feel anything because we stay in motion. If we're in motion, we stay in motion unless acted on by a force. In the same way that if you're in an airplane, you feel normal, even if you're going 500 miles an hour, because even if you're going really fast, you don't feel it. You stay in motion without a force having to act on you. He also built now it wasn't the first telescope, but it was one of the first good telescopes, and he discovered a whole bunch of things. He discovered the moons of Jupiter. Okay, we call these the Galilean moons after Galileo. Okay, by the way, Galileo Galilei is kind of funny. His first name is the same as his last name, basically. I actually meant to pull up a quote. There's someone making fun of him from back then. But anyways, he discovered the 4 moons of Jupiter, which was cool because back then, if everyone thought all the planets orbited the Earth, this was a little bit of evidence that, hey, stuff just orbits stuff. You have moons orbiting Jupiter, Jupiter orbiting the sun, you know, Earth orbiting the sun. It's not that everything has to orbit the Earth, stuff just orbits stuff. He also discovered the phases of Venus. We'll talk about this in a second because this is important. Because this is actually pretty strong evidence for, well, against geocentrism. He refuted ideas about everything being perfect spheres. He saw sunspots. He saw craters and mountains on the moon. Because a lot of the arguments about everything have to be in perfect circles and spheres was that everything was perfect. But he refuted that. And finally, he correctly argued that stars are just so distant that we don't observe parallax. Okay? So he kind of knocked down most of the arguments against heliocentrism. Again, along with this theme, he published a big dialogue kind of trying to argue his points. He was ordered to stand trial by the Catholic Church, found suspect of heresy and forced to recant by the Inquisition and placed in house arrest for the rest of his life. To be fair, he was poking kind of undiplomatically at the time, but he nonetheless, I mean, it just shows you the resistance of dogma or dogmatic resistance to new ideas that's based in really wanting to believe that it was the Earth that was the center, not the sun. Makes things difficult for scientists who are just trying to follow the data. Here's so his was one of the very first telescopes, and this we'll see many more beautiful pictures later in the course of Jupiter and its moons, but this is just one taken with a digital camera. You don't need a good telescope to see Jupiter and its moons. You can actually see them with a very, very cheap telescope or even a zoom on your camera. So this is the sort of thing that Galileo would have seen, something that looked like this. And he observed the phases of Venus. The same way the moon can have phases, Venus orbits the sun, okay? And it's in an inner orbit compared to us. So if it's on the far side of the sun, it should be full. If it's on the near side of the sun, it should be new Venus. And he observed the phases of Venus. And if you think about it, if we had a geocentric model, then it would be the sun that orbited Earth, and Venus would be going in little epicycles maybe, but it would never be moving. It would always be on the close side of us to the sun, so we'd never see a full Venus. Okay, and so his observation of the phases of Venus pretty much refuted the idea, well, many of the geocentric models. Okay, so quick recap. Copernican revolution. Copernicus, Polish astronomer who came up with one of the first really detailed predictive heliocentric models. Tycho Brahe was a big figure because he made really, really careful measurements that then allowed Kepler, his German assistant, to formulate his 3 laws of planetary motion, including that planets follow ellipses, not just circles. And then Galileo made very compelling arguments. He built a telescope, discovered moons of Jupiter, and argued forcefully for the Copernican revolution, which around that time, views were starting to shift towards this new view in which the Earth was not the center of everything. In fact, since then, it's been shifting further and further away from that view, more towards that we're just one planet orbiting kind of an ordinary star out of literally billions in a kind of ordinary galaxy out of billions of galaxies in no particular special place in the universe. Any questions about that history, that little history too? So again, this is kind of a cartoon. You can spend a career talking about the scientific method, but the basics are that you want to theorize, but then you make predictions. You have to make predictions to try to hold your theory accountable to experiments. Okay, so you do experiments, you analyze the results. If they're in conflict with your theory, you revise the theory. You don't make too many excuses to try to hold on to your theory. Like, for example, that you want everything to follow perfect circles, so you keep making excuses and you add epicycles. No, it might be pointing you to try a different theory. And I'm going to talk about some things that are good guideposts for understanding what science is and how it works. One is that science is built on the bones of dead theories. So as an example, I'm going to answer this myself, but is it possible to tell with absolute certainty how an atom looks, how an atom doesn't look, both, neither? Well, the modern view is that we can't tell with certainty how an atom looks. We can never know with certainty how an atom looks. What we can do is keep throwing out bad theories of how the atom looks. We can keep ruling out ways in which it doesn't look. Okay? Over time, we increasingly understand the natural world better, but it's always going to be approximate. It's never going to be perfect. Okay? But we keep ruling out more and more. And scientists embrace this. So science, I mean, it's something to celebrate when a theory gets proven wrong, or the word we're going to use is falsified. If you see something wrong with a theory, that's good. That means you're getting better. It's kind of exciting in science. We don't try to keep theories correct. We always are excited when a theory is wrong. That's progress. This is just one piece of this whole discussion of science, but I'd say if I had to think of one rule that most scientists think is more or less right in terms of explaining what science is, it's Karl Popper's falsification criterion, okay? And it's this: a theory which is not refutable, if you can't refute a theory, that's non-scientific. In other words, if something's irrefutable, that's not a virtue of a theory, it's a vice. Okay, that's because, well, we'll see examples, but you might think that something that's irrefutable is good, but as we'll see that that's actually very, very sloppy way of formulating a theory. If you want to test a theory, you need to attempt to falsify it, to refute it. In other words, to test a theory is to try to falsify it, to try to put it to the test. And there's degrees of testability. Some theories are more testable, in other words, more accountable to data, more exposed to refutation than others. They take greater risks. So you want a theory to take risks. You want a theory to put itself out there so that it can be proven wrong. And that's a scientific theory. So it might help to talk about examples, right? So an unfalsifiable theory is one that doesn't make new predictions, for example. So you can come up with a theory that gravity is due to angels pushing things around. That's fine, could be true, but if it makes the exact same predictions as the current theory, you've just added some complication that has there's nothing you could possibly test, right? If these are invisible angels and you can never test them or falsify them, then they don't add anything to the theory. So that would be unscientific. Another example would be young Earth creationism. Now, this would be the idea that, in science, we see all this evidence like bones of dinosaurs going back millions of years, and so on. But it could have been that they were all placed there, like God created and just placed all the bones to look like it was old. Again, that's possible, totally possible. Doesn't mean it's wrong, but we call that unscientific because there's no way to falsify it, right? Any piece of evidence that you have, you could say that, oh, that was placed there by God to make it to mislead you, right? So it's impossible to falsify. So that's unscientific. Another example is vague or open to interpretation, right? Does not hold itself accountable to clear or definite predictions, like astrology, right? The horoscopes, right? The idea that the month you were born determines your personality, for example. If you go to an astrologer, and I've gone to an astrologer, they'll make predictions. They'll tell you about how things are going to go for you, but they are very vague. They don't hold themselves accountable to any way they could be falsified. The words they use are open to interpretation, and you can't right? You can't get lottery numbers out of them or anything useful. It's all vague things. Homeopathy, that's an example of a medical idea where you give people tinctures that the problem is you go see a homeopathist and they'll give you a tincture and they'll say, well, this might take a day to work or it might take a year to work. Everyone's different. And if it doesn't work, they'll say, oh, well, you're different, so we'll make up a new tincture for you. And there's no way to hold it accountable. It can't be falsified because anytime something doesn't work, they come up with a reason. So again, it's not bad necessarily. I think that is dangerous, but the point is that it's an example of something we say is not scientific. Finally, I'll give another example. Conspiracy theories are unscientific. They're unscientific because any evidence you come up with is dismissed as part of the conspiracy. I don't know if I've argued with conspiracy theorists before, and it's frustrating because any piece of evidence, right? It doesn't matter how good your evidence is you come up with. Ultimately, they can always dismiss it as being, oh, you're part of the conspiracy, or the astronauts that came back and claimed they saw the round Earth, part of the conspiracy. NASA's part of the conspiracy. So there's no way to falsify it because there's always an excuse. So anyways, I hope I've conveyed kind of the heart of what makes science science. What is science? It's trying to hold theories accountable, trying to falsify them, not trying to make them be right, not trying to be sneaky and make slippery, but to actually try to show that your theory is wrong. That's the spirit of science. You want to put it in the fire experiment. So I'll leave you with just one example. If I hold out my hand and drop a coin and it falls to the ground, which of these two theories are scientific? And this gets the point across. That doesn't mean which one's right necessarily. It's just which one's scientific. So you can say, I hold out my hand and drop a coin, And one of the theories is it's the will of Odin, okay? And another theory is that, well, on odd numbers days, it falls up heads. On even number days, it's tails. Well, B just sounds silly and wrong, but that doesn't make it unscientific. It's a perfectly scientific idea. Now, it's scientific because it can be shown to be wrong. You can test it. You drop the coin and you see if it comes up heads or tails. And if it's wrong, that's great. Perfectly scientific. It just turned out to be wrong. Whereas A, it is the will of Odin. I can't think of any way to falsify that. Okay? No. That is an example of an unfalsifiable example A and a falsifiable or scientific supposition B. All right, I think that's about where I am. Yeah, so that finishes lecture 4. I'll leave it there today. Are there any questions on this material?
I have a question.
Go ahead.
There's no homework except for just reading, right?
So this would be a good opportunity, since we have a few minutes, for me to just, since only 50% of people sign up for the homework, let me just quickly go there and just show everyone off, show everyone, since I'm screen sharing right now. I can just sign into Mastering Astronomy. Go to my course. And so everyone should have a page that looks something like this, where I'm waiting for it to load, where they can go to the calendar here. Calendar. And so you see that there was homework due on the 20th, chapters 1 and 2, and that 2 days from now, chapter 3 homework is due. Okay. So you have a homework due Wednesday night, and you'll see all the homework here. So if I go to the next month, I can see it all laid out. I have all the homework out pretty much every week, laid out all the way till the end of the course. We skip 1 week for spring break, but I think it just continues, yeah, every week. All right, and you can get started on it early if you want, although it's nice to go along with the lectures because I've been keeping them kind of in tune with the lectures. But if you want, you can just go ahead and do as many of them now as you'd like. All right, and remember, okay, since we still have a few minutes, I can do the same thing for D2L. If you go to D2L, for the quizzes, click on quizzes up here, and you see, now you will see just the ones that are, so you will see quiz 2 is the next one, available January 26th until January 29th. So starting tomorrow, available until 3 days after that, okay? Now we'll be covering some of stuff, including today's lecture. And then finally, the other place is I have this website, and all these links are on D2L. And this, if the schedule ever changes, I'll update it on here. And this shows every day. So here we're on the 4th day. So we just did lecture 3. I'm sorry, we're on the 5th day. We did lecture 4. It's the 4th day. It's the 4th day of actual lecture because this was a holiday. And we did lecture 4, and there's the PDF of the lecture here. And it also shows that there's going to be a quiz this week. And it shows your readings. And you can see that all throughout till the end of the course. All right. Any other questions?
For participation, we're graded by doing the polls, right?
Yeah, so that's 25% of your grade. And yeah, you're graded just on your performance on those polls, 2 or 3 questions a class. And I try to make them so that if you're just paying attention, you should get an A on the poll part of it. But some people just leave their computers, you can tell, because they either answer randomly or don't answer at all. So, all right, any other questions? All right, I will see you Wednesday. Bye.
Thank you.
Thank
Thank
you.
Have a good one. Thank you.
Okay.
Mandy!
Hmm.
No. I eat baby food.
Oh my god.
It's good. You want to try some? Can I have your new phone now? Mandy, can I have your new phone? Oh my god, go away, go away. No, oh my god, go away. Yeah, fucking number one. What am I glad for? Go, go, go!